So we just sort of finished talking about alkenes, and alkenes, as we just saw, one of the reactions of an alkene when you take the double bond like we were talking about and we add water to it, as we saw, this double bond will become a single bond. And we will add an OH in there. And what we do make is an alcohol. So one way that you can produce an alcohol is through the hydration, which is what this reaction is called because we're adding water. Just adding water here. We could form an alcohol. So an alcohol is an organic compound that has the functional group of the OH. So that OH being there is what makes it an alcohol. And as we'll talk about, that is much like all other functional groups, kind of really the important part of the structure there. It is a polar bond, as we talked about in bonding. So that OH bond is partially negative on the oxygen, also partially positive on the hydrogen. And that gives alcohols a slightly different property than alkanes. They actually can interact with water through hydrogen bonding. So water, which is also positive and negative there on the oxygen, the positive hydrogen of the alcohol. I missed it completely and drew it to the positive sign there. Let's try that again. Let's actually make them connect. Maybe that would be better. All right, so the positive there, the hydrogen, will be attracted to the negative there of the oxygen and the water, and they can do what is referred to as hydrogen bonding. And that means that alcohols that are about maybe less than 5 carbons or so that have the OH group on there are fairly soluble in water, so they'll mix really well with water. But when you get kind of above 5-ish or 6 carbons and more, what happens is you build out too much of the nonpolar side of alcohols, and it's just too big to interact with water. So even though it has that little spot where it can interact, it's very, very kind of hidden from being able to interact well with water. So small numbers of carbons that have the OH as an alcohol usually are fairly soluble in water. But the solubility of it does start to really decrease as you build out a ton of carbons. Again, usually about 5, 6 or more. You really start to see the solubility decrease a lot. The way that we name alcohols, not surprisingly, is the exact same way that we name everything else. It all goes back to the alkane names. The priority, though, in terms of sort of naming and numbering, the priority here is going to be the OH group. So much like when we were counting the longest carbon chain with alkenes and alkynes that had to have the double bond or triple bond in it, the longest carbon chain here has to have the OH group attached to it. So it's got to be part of the longest carbon chain. It will match one of those alkanes based on how many carbons there are, and it will end in OL, basically. So he dropped the last part of the alkane name and put OL. Just like what we did with our double bond and triple bonds, you do need to give the location of where the OH group is starting around 3 carbons. So you do need to give the location of the OH group, which is basically the number on which carbon it's attached to, around 3 or more carbons. So the simplest alcohol you could have is this guy right here. This is 1 carbon and it has the OH group. That is based off of methane, and that is known as methanol, OL. The next simplest one you can have is really 2 carbons. that has the OH group attached. 2 carbons is based off of ethane. This is what is known as ethanol, OL. Now, when you get to 3 carbons, you could have the OH group there. Or you could have, say, the OH group there. Now, because we got 3 carbons, and in each of these cases, the OH group is actually attached to different carbons. There's options, obviously. This is where we need to start giving the number as to where the OH group is attached. So we would do the same thing as we did with, pretty much the double bond and triple bond. This would be 3 carbons, which means the base of the name is based off of propane. And it becomes propanol here, OL. We always want to give the OH group here, because it's a functional group, the smallest number, which means the smallest number would be, in this case, 1, right? We would start numbering right to left. And this would be what is known as 1 propanol. 1 propanol, the 1 means the OH group is at carbon number 1. That means that this guy below it would be called what? It would be 2 propanol. It still has 3 carbons and the OH group, which makes it propanol. But the OH is at carbon 1 and 2. And it doesn't matter which way you go, 1 and 2, right? They both end up there basically at 2. So this is 2 propanol, which, by the way, as I think I might have mentioned earlier, also known as isopropyl alcohol and also known as rubbing alcohol. Because if you look at it sort of in its condensed formula, you can maybe see it easier. That's CH3, CH3, OH. That's that isopropyl group we talked about when we were talking about groups. And since this is an alcohol, it's sometimes referred to as isopropyl alcohol. Its official name there is 2-propanol. Its unofficial store name is rubbing alcohol, basically, right? That's basically what that is. So they're all the same thing. So 3 or more carbons, you need to give the location of where the OH group is at. Also very similar to our double bonds and our triple bonds. Once you decide which way you're going to number it, based on giving the OH group the smallest number, everybody else that's attached, if there are other things attached, are numbered accordingly. So once again, you got to choose one way to number and keep it for everything. So let's take a look at one here. Why don't you name, I don't know, I'm just randomly drawing things here. All right, what did I just do? I don't know. What is this here? All right, why don't you give that a try, and I'll hope for the best there and give that a number, a name. Why don't you also give this a name, what you think it might be? And why don't you draw 3-pentanol? And why don't you draw 2-chloral 2-butanol? In the drawing, you want to do the same things we did with everything else, work backwards. In this case, it would be, I think, circling all the way around here. So that is the longest carbon chain that has the OH attached to it. That is 1, 2, 3, 4, 5, 6. So it has 6 carbons with an OH group attached to it, which makes it an alcohol. So that's going to become hexanol. We do need to give the location of where the OH group is. And again, we want to give it the smallest number, which means we should number, in this case, left to right to do that. That would give us 1, 2, 3, 4, 5, and 6. If you went the other way, the OH group would end up with a 4, right? And so that'd be larger. So this is 3-hexanol. Again, the 3 is where the OH group is located. That means the only other thing that's there is a bromine group, right? Or a bromol group. And because we locked in our numbering going left to right, that means the bromine there is at carbon number 4. So this would be 4-bromol 3-hexanol. Any questions on that name there? All right, so if we look at the next one, pretty much the guy that has the OH is this whole ring here. And that is 6 carbons, which is cyclohexane. Because it has the OH group, it would then become cyclohexanol. Yeah, OL. Now, we do have a methyl group hanging off here, and we do need to give the location. And because the OH group always gets the priority in terms of the numbering, because it's in a ring structure, that OH group has to be carbon number 1. And now we want to go either clockwise or counterclockwise to give that group the smaller number. And just looking at it, it looks like clockwise would give us the smaller number there going that way. Going the other way, it looks like we'll end up with 1, 2, 3, 4, 5. So obviously that's a larger number. So this would then be 5-methyl cyclohexanol. Any questions on that one there? All right, so we're going to draw this going backwards like normal. So pentanol, the pentane part, tells us we should have 5 carbons. OL tells us it's an alcohol. And the 3 tells us where the OH group is attached. So it's attached to carbon number 3. I'm going to go left to right. So that's going to be my carbon 1. So this would be OH. And that's pretty much everything. So now we're just going to put our hydrogens in. That's going to be 3 hydrogens, 2, 1, 2, and 3. And that obviously would be our condensed formula here. If you wanted a little line action, you would do the same thing. You would start with the 6 carbons, 1, 2, 3, 4, 5, and one more makes 6. So 1, 2, 3. Do an OH. Yeah. So, yeah. For which one? It is 3. It is 3. Thank you. I think I said 5 going the other way, and then I wrote 5. I think. Thank you. No. Again, just making sure you're awake out there. Thank you. I'm making sure you're awake out there. Just it is. No, me either. That's like obviously. Thank you. I think I was counting 5 the other way, and I wrote 5. Sorry. It should be 3 for sure. Yeah. Other questions on that? Okay, coming here, that's butanol, which means that's 4 carbons, 1, 2, 3, and 4. Once again, the OL tells us it's an alcohol, and the 2 tells us where the OH is at, and that would be carbon number 2. So I'm going to put it here, and that's going to take care of that part of the name. We also then have a chlorine at carbon number 2, which means I would put a Cl there. That would take care of that part of the name, and everything else would be hydrogens here. So that needs 3. That needs 2. Guy in the middle needs none, and this guy needs 3 in this case. Any questions on how to name alcohols, draw alcohols? I got all the numbers right, except I wrote the wrong one. It's not bad. Okay, then let's talk a little bit about the major reactions that alcohols undergo. Alcohols kind of go under redox reactions, which means the that is a oxidation or reduction sort of situation. And if you remember, oxidation means loses electrons, reduction means gains electrons. But really in the organic sort of realm, we really don't kind of look at electrons. For oxidation, we look at either gaining oxygen as you go from reactants to products, or losing hydrogen as you go from reactants to products. So those are really three definitions. Get rid of this out of the way here. These are really three definitions of oxidation. And really in organic chemistry, we do kind of focus in on these two definitions. While reduction means obviously gaining electrons, the losing of oxygen as you go from reactants to products are the gaining of H2 as you go from reactants to products. Once again, in organic chemistry, we really do sort of focus in on those two definitions for reduction. And oxidation is either gaining oxygen or losing hydrogen, while reduction is losing oxygen or gaining hydrogen as you go from reactants to products. Now, alcohols can be classified the same way that we classify carbons as primary, secondary, or tertiary alcohols. And that means that if I had an alcohol, say like this, I would look at the carbon that has the OH group attached, and directly attached to that carbon is one other carbon. This would be a primary alcohol. If I had an alcohol such as this is the carbon that has the OH group attached to it, and directly attached to that carbon is one carbon and two carbons. And that would mean that this one is a secondary alcohol. And lastly, you could have an alcohol where you got this situation happening. And again, looking at the carbon that is directly attached to the OH group, we would see that it is attached to 1, 2, and 3 carbons, and that would be a tertiary alcohol. Any questions on how to identify those? So very much like how we identified the carbons, but in this case, we have to look at the carbon that has the OH directly attached to it, and then we're looking at how many carbons are attached to that carbon. Again, sometimes people count hydrogens instead, but I think carbons counting is a little bit easier than hydrogens as well. Now, classifying the alcohol is really important in terms of the reactions that these alcohols undergo. So depending on the type of alcohol it is, it will go through a certain type of reaction, and it'll be different than, say, a secondary alcohol versus a primary alcohol. So let's talk about the reactions that each of these sort of undergo, these oxidation reduction reactions. And we'll start with the primary alcohol first. So the primary alcohol, we'll use that one as our example there. We'll do this. I'll just draw out everything here. So this is our ethanol, which is a primary alcohol. And what happens when this goes through a oxidation reaction, which is sometimes abbreviated with this little O in a box type of thing, which means oxidation, is it is going to actually go through the definition of losing H2. So it's going to lose H2 is what's going to happen here. Now, where does the H2 come from? It always comes from the same two spots. And it's very similar to if you think about what we just talked about, which was when we added H2 to a double bond, right? A hydrogen went to one carbon, right? And the hydrogen went to the other carbon, and the double bond disappeared. In this case, what's going to happen is you will always lose the hydrogen from the OH, and you will always lose one hydrogen from the carbon that's attached to the OH. So those are always the two hydrogens. Those are always the two that go away. Now, pretty much just like anything else, everything else in that molecule outside of the two highlighted guys are going to stay exactly the same. So you're just going to redraw it exactly the same. So we're just going to sketch it exactly the way it is. Obviously, we lost two hydrogens, which means H2 comes off, basically. They get the two hydrogens off. Now, when we put hydrogen on to a double bond, right? The double bond went away, right? So if I remove the hydrogens, the double bond then comes back, yeah? And that's what happens. We will always make it then a double bond between the carbon and the oxygen. And that's where we remove the two hydrogens. That's a really bad double bond. Let me just draw it over there. We will then double bond up there, better than I just did there, between the carbon and the oxygen. And what we make here is a new organic molecule, which is known as an aldehyde. And an aldehyde has this functional group, the carbon oxygen double bond, and the hydrogen. It is this guy at the end, is what makes that an aldehyde. So if you oxidize a primary alcohol, it will make a aldehyde as the result of it. By the way, the reduction reaction is the opposite. It goes that way. And the reduction reaction, the hydrogen goes here, hydrogen goes here, and the double bond goes away. So it's really the opposite. So you could add hydrogen to an aldehyde and you will get back an alcohol. But in this case, the alcohol will be oxidized to an aldehyde in this case. Any questions on that there? Now, if we take a secondary alcohol, so let's draw a secondary alcohol here to start with. Let's do we'll do this guy here, which is a secondary alcohol. So this is a secondary alcohol. Once again, if we look at the carbon here that's attached to the OH, it's attached to two other carbons. And if we put this guy through oxidation reaction, once again, what's going to happen here is we're going to lose H2. And just like before, the H2 is going to come from the exact same location, which is the hydrogen that's part of the OH and the hydrogen that is part of the carbon that's attached to the oxygen. So once again, those are the two that always go when this happens. And just like we did before, I'm going to redraw this exactly like that, but just take out the two hydrogens, basically. So I'm just going to redraw. And since the two hydrogens came off, we will also get H2 that comes off. Once again, just like we did in the primary alcohol oxidation, what do you think I should put between the carbon and the oxygen? I should make it a double bond. Yeah, so we're going to make it a double bond right there. And this makes another type of organic compound, which is known as a ketone. And a ketone always has this as a functional group. It is a 3-carbon run where the middle carbon has the carbon-oxygen double bond. So that is what you need for a ketone, is that carbon, 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 3 carbons in a row. Middle guy has the double bond at the end of it. By the way, if you want to reverse it, you just add the H2 back, and it's the reduction reaction going in the opposite way, and you'll get your alcohol back. Now, if we look at a tertiary alcohol, so let me draw one of those guys there. We'll do We'll just build off of this guy. And we want to do an oxidation of a tertiary alcohol. And again, that is the carbon in the middle that's attached directly to 3 other carbons, which makes it a tertiary alcohol. We're going to lose H2, which means the hydrogen should come off of the oxygen, right? And the other hydrogen should come off of which thing? Should come off of the carbon, right? That's attached to the oxygen. Is there a hydrogen there? There's not a hydrogen there. So because it actually lacks the second hydrogen that's necessary, it will not go through oxidation. You'll get no reaction. So you actually will get no reaction in this case. And that's because the carbon is missing the second hydrogen needed. We have one, but the carbon there in the middle doesn't have the second one. So you actually get no reaction. So you cannot oxidize a tertiary alcohol. You get pretty much nothing. It just stays the same. So primary alcohol, when it oxidizes, lose the 2 hydrogens, one from the oxygen, one from the carbon, make a double bond between them. You get an aldehyde. Secondary alcohol, lose the hydrogen from the oxygen, hydrogen from the carbon, double bond between them. You get a ketone. Tertiary alcohol, you get nothing. Basically, no reaction that occurs. Question on any of that there? So why don't you try one here? A couple. Let's do. Okay, why don't you oxidize this guy, and why don't you oxidize this guy? Then why don't you oxidize this guy here? You're doing so when we're looking at an alcohol here, which we could clearly see, we also know that this is pretty much the area that's going to change. We want to maybe identify what type it is, so we have an idea maybe what we should end up with. This is what type of alcohol. This is this carbon, which is attached to the OH, is attached to how many other carbons directly? One there and one there, means this is a secondary alcohol, which automatically I know will go through oxidation. I should end up with a ketone. It's good to know where you need to end up, right? So once again, nothing's going to change other than what we talked about, which means because this will go through oxidation, I'm going to take off an H from the O and an H from the carbon that's attached to the O, and everything else remains the same. So I'm just going to copy it. So I got CH3, I got CH2, I got a carbon, I got no hydrogen there, but I'll go down, CH3. And get rid of that there. And then going up, I will still have oxygen. Is left. Delete it, and then I bet want to try that again. I have my carbon, and I will still have my oxygen. And much like before, I should do what between those two? Make it a double bond, yeah. And again, we'll have the H2 that will come off if you want to put it in there. That is our ketone, and this is the ketone part of it. It is the 1, 2, 3 carbons where the double bond there is on the second carbon. If you want, you can straighten out the carbon there and just draw it straight. You can do that as well. Or you can leave it like that, however you want to do it. Any questions on that one there? Once again, I'm going to focus in here over here. That would be what type of alcohol? So this is the carbon, right? That is attached to the OH. It is directly attached to a carbon here and a carbon there, right? Which means it's actually 2 carbons attached to it, which means this is actually also a secondary alcohol, which should also give me a ketone when everything's said and done. In this case, I'm going to draw everything the same, and I'm going to take away the hydrogens. In this case, this is line structure. You can just take away the hydrogen off the oxygen and assume the other one's gone. What should go between the oxygen and the carbon? Yeah, we're just going to double bond it up like that, yeah? Now we have a ketone that's there. The ketone part of this is 1 carbon to 2 carbons to 3 carbons with the double bond hanging off the side there, the middle carbon. Yeah. Any questions on that one? Last alcohol on the bottom, primary, secondary, tertiary alcohol here. Focus in here. That carbon is attached to how many other carbons? There's only 1, right? That one that has the OH is attached to that carbon there. This would actually be a primary alcohol, right? Which will go through oxidation. It should make a aldehyde, right? So even before you draw it, you know what you should end up with. Once again, everything's going to be the same, except I'm taking out my hydrogens. So I'm going to take out my hydrogen there and 1 attached to the carbon. It really doesn't matter which one you take. I'm going to copy everything exactly the same. CH3, CH2, 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 C, H, and O. And I'm going to then finish it up by double bonding my carbon oxygen. There would be H2 that would come off in each of these here. Any questions on how to draw those? So oxidation of an alcohol, H off the oxygen, H off the carbon that's attached to the oxygen, double bond up between carbon and oxygen. Yeah. Everything else stays exactly the same. Do not move anything else. Just do those 2 things, basically. Any questions on those there? Question on alcohols. All right, then let's talk about actually these 2 guys here a little bit here to finish up with. Let's talk about aldehydes and ketones. Aldehydes, as we just saw, has a functional group of carbon, oxygen, double bond, and hydrogen. Ketones has the 3 carbon run with the double bonded oxygen there in the middle. As we just saw, you could make each of these from an alcohol. So from a primary alcohol, as we just did, you could oxidize it to an aldehyde. And by the way that we name aldehydes is it ends in Al, not OL like alcohols, but Al. This guy has 1 carbon and 2 carbons, which means this is what is known as ethanol, Al. Yeah. You do not need to give the location of where that carbon, hydrogen, carbon, oxygen double bond is, because the aldehyde group will always be at the end. It'll be at one end or the other. It's got to always be at the end because of the hydrogen. Hydrogen can only have 1 bond, right? Which means it can never be in the middle. So at the end, which means you don't have to give the location where the carbon oxygen double bond is, but it is assumed to be carbon number 1 for naming things. So for example, if we had this guy here, and we'll just put like a chlorine there, maybe a methyl group there, and we'll fill in here. So we would still look for the longest continuous carbon chain. That would be in this case 1, 2, 3, 4, 5 that contains this guy, right, which is our functional group. You could also get 5 going down from the top guy as well if you wanted to. So 5 carbons is based off of pentane because it has this aldehyde group. This is known as pentanal, AL. Now we do call this, excuse me, we do call this carbon number 1, carbon number 2, carbon number 3, carbon number 4, and carbon number 5. There really is no choice here. You got to start where the carbon oxygen double bond is with the aldehyde. So that always is going to be carbon number 1. That means at carbon number 3, we have a chloral. And at carbon number 4, we have a methyl. And just like before, alphabetical order here, this would then be known as 3-chloral, 4-methyl, pentanal. Any questions on that name there? So always it's on the end, and that always is carbon number 1. And same thing, if you were to have to draw it, you would just work your way backwards with the name. So if you were going to draw one of these aldehydes, let's take a look at one of those here. We'll just do, I don't know, we'll do 3-bromyl. I will do hexanal. So if we were going to draw this one, we will go backwards. So hexane tells us 6 carbons. So that's what we would start with. Get 6, 1, 2, 3, 4, 5, 6. Al tells us it's an aldehyde, which we know the functional group is this. Now, once again, since you are drawing, you could put that group at the very last end, or you can put it on the left side, right side, it doesn't matter. I'm going to put it at the end, but you do use the carbon that is there. So we're going to build that group off of the last carbon here at the end. We're not going to add an additional carbon, otherwise we will end up with 7 carbons, right? Too many. So we're just going to build it off of there. So that is our hexanal. And once again, because of that, it has to be carbon 1. This would be carbon 2. This would be carbon 3. That would give us our Br. And putting in our hydrogens here to fill it out would give us our aldehyde. So you basically build it the exact same way as you do anything else. The key is you got to use the carbon that's already there from the longest carbon chain and build the group on the end. Again, could do right end or left end, it doesn't really matter. Question on that one there? So let's talk a little bit about the ketone here as well. As we also saw from a secondary alcohol, we were able to make a ketone here, basically. Do this guy here. So once again, by oxidizing this, we were going to remove this and this guy. And that is our secondary alcohol coming into a ketone. And again, the ketone part of it is the 3 carbons in a row with the OH group right there. Ketones are named by having ONE at the end of it. So this is 3 carbons. This is what is known as propanone, ONE. 3 carbons for propane. When you get to about 4 or more carbons, you do need to give the location where the double bond is, carbon oxygen double bond. unlike the aldehyde, which is always at the end, this guy will never be at the end, the carbon-oxygen double bond, because it needs those 3 carbons in a row, so it'll never find the carbon-oxygen double bond at the end. So if we had something like this, and we wanted to name it, we would again find the longest continuous carbon chain that has the OH in it. So that's the double bonded oxygen, which is here. So that is 1, 2, 3, 4, 5, 6 carbons. 6 carbons is based off of hexane. So this would be known as hexanone. Because this is more than 4 carbons, we do need to give the location of where this guy is at. And going left to right, that'll be carbon 1, carbon 2, carbon 3, 4, 5, 6. Going right to left, that would be 1, 2, 3, 4, 5, 6. We always want the smaller number, which means we should number this way, which means that this would be known as 3 hexanone, right? The 3 is where the carbon-oxygen double bond's located. And because we locked into place numbering this way, our chlorine will have to be number 5 in this case. So this would be 5 chloral 3 hexanone. ONE. Question on that. So again, the functional group gets the priority, and you want to number it whichever way gives the functional group the smaller number when you're dealing with the ketone. And then all the other groups obviously need to be numbered accordingly, whichever way you choose. Question on that there. One very last thing, and then I'll let you go. We saw with our primary alcohol that you could obviously oxidize it to an aldehyde. And I'll just make an aldehyde here. Let's do and we saw with our secondary alcohol, you can oxidize it to a ketone. You can continue to oxidize the aldehyde one more time. And when you oxidize the aldehyde one more time, it's actually going to gain oxygen. So we're not going to lose hydrogen here, but we're actually going to gain oxygen. And where it will always end up, it's like a mystery right there. Where it would always end up is the oxygen will always go right there. So it'll always just find its place right there. Nothing else will change. So this guy would be CH3, CH2, C double bond O, and we're going to put our oxygen in there and make an OH at the end of it. And that is what will always happen if you oxidize an aldehyde. It makes this guy right here, which is known as a carboxylic acid, which is another organic group. So you could take a primary alcohol, oxidize it once, lose 2 hydrogens and make an aldehyde. You could oxidize it one more time and you make a carboxylic acid. Why this is important is if you oxidize a ketone, you get nothing. Yes. So because it's missing that hydrogen that's sort of necessary, it cannot kind of go through the oxidation. And why this is important is if you had to choose or try to figure out, do you have an aldehyde or do you have a ketone? Only the aldehyde will be oxidized. And there is a reagent that is used sometimes, which is known as Benedict's reagent. And basically it is a copper 2, actually it's blue to start with. The copper 2 is blue. We'll do that. We'll do our copper 2 is blue. So blue solution. And if it finds a carboxylic acid present, We'll actually turn that color there that we saw, kind of this orangey red color. And it will reduce to copper +1. And that would be a positive test for a carboxylic acid, which means if you were testing unknown samples and you did it, but you knew you were doing an oxidation reaction and you saw the oxidation reaction happen and this reagent go from blue to this orange to gross looking red color, depending on how it's been out there, you would know that you actually started with an aldehyde. If you did this reaction, you added Benedict's reagent and it stayed blue, you know you would have a ketone because the carboxylic acid wasn't made. So Benedict's reagent is used to identify the presence of a carboxylic acid, which in the case of your lab means that you started with an aldehyde. And if it's a negative test for Benedict's reagent, it means you probably have a ketone in that case. Any questions on that there? All right, well,